Okay, cool. The much awaited game AI Architectures Lecture Part 1. Starting now. Uh, a lot of the stuff that we talked about so far is really kind of in the ether of like, okay, here's some ideas of algorithms, maybe some behaviors, things like that. But ultimately, this has to distill down and be used in a system. And often that means you have to kind of build out an architecture within the context of your game and actually bring it into fruition. And so, what we're going to dig into some of those approaches, both from the perspective of a design and architecture standpoint, but also in production, and some of the kind of considerations that go into these things as you start to think about how to apply these ideas to your games. So let's kind of think about the context of agent behavior, or how do we kind of make an agent in a game make decisions and behave in such a way, right? There's a very big difference in sort of context here. For example, the kind of AI system that you might want to design for a first-person shooter is going to be fundamentally different than a AI system that you might be designing for an RPG. So this is something that you really kind of have to think about the differences in the needs and requirements of your game. Like, for example, right here's a very simplified counter-terrorist bomb example decision tree, right? And you can kind of see it sort of looks like a relatively simple finite state machine with essentially these conditional Boolean sort of decisions that are made to then result in the green action to take given the state of the game. So, for example, you start off, is the bomb planted, yes or no? If no, am I a sniper? If so, I'm going to go set up as a sniper. If no, has the bomb been dropped? Like, I'm going to look for the bomb, right? Like, there's this whole series of conditional statements, or what's called an expert system, that tries to codify the state of the environment into a resulting action that particular agent needs to take given that state. And so it's almost like a filter, like a sieve, that things kind of come through, and by the end, the marble ends up in a particular place, and you take that action, right? So this is kind of one way to determine what to do that's relatively straightforward. All right, so the code, right? What does the code look like for a basic tree like that? For a small set of scenarios, it might just be a bunch of if statement, just a nested if statement, a multi set of conditionals. But for a larger thing, you might want to have a true graph type of architecture with many edges, maybe even have probabilistic edges. Maybe it looks more like a Markov decision process. You might want to store this in an array, or perhaps in a memory structure like a heap or a binary tree. There's a lot of kind of considerations about how to actually turn this into implementation. For example, right? What if you were to use a design pattern like the strategy design pattern? Let me just take a moment. Sorry, I just had to brush up. I'm not familiar with the term strategy design pattern, but what the strategy design pattern is essentially this kind of decoupling of the task and algorithm. And the reason this is valuable, right, is if you have a particular task like sorting, you want to sort a list, but there are different strategies to sort a list. You can use quick sort, which is great, but has like this sort of recursive thing that you might be worried about, or just a linear bubble sort. Bubble sort might actually be faster for, say, you're sorting 10 things versus a million things, and so you may have different strategies for different kinds of scenarios. And so from a design pattern standpoint, what you do is you create a sort kind of interface, right? And when you actually call this function, this pattern then takes over and calls an algorithm. The algorithm then automatically determines which actual algorithm to use, be it quick sort, bubble sort, or Doge sort, or whatever else you want to use. So this is kind of an interesting way to abstract out how these things are actually implemented, right? So you can just call the same function, but it does different things in different scenarios. Pretty cool. Okay. This should have just moved to the next slide. But that's what I just said. So for example, you could have a player class and it has a bunch of different actions, right? And and then basically depending on the scenario, you choose the action. That's kind of a limited code example, but okay. So decision trees are very common for AI behavior. This is something that we just saw before. This might not look like a tree, but it is, right? Because at every one of these, I can't draw, can I? But that's okay. At every one of these crests, that's kind of a line, and that would be a depth of the tree. This is literally a binary tree because it's got two possible edges for every option. Some things are leaves, and those leaves are actions, and some things are nodes, and nodes have, leaves or other nodes, as you know, binary trees, standard stuff. Right? So kind of you can feel free to pause and think about, well, what are the benefits of such an approach, and what are the drawbacks, right, of such an approach? Hopefully you paused and thought about it for a minute, right? So the benefits of the approach are pretty clear. It's quite simple, and it's somewhat deterministic of what's going to happen given a state, right? You can propagate the state through the tree and get to an action. Also, the downsides is that it's deterministic, right? Like AI, I'm sure all played a game that has, AI that's built on a decision tree, and you can kind of trick the AI into doing silly things, or find a place in the game where like moving slightly to the left makes them do certain things, and moving slightly to the right makes them do other things because of this sort of discreteness in the state, in the decision tree state and transition dynamics. So there's a lot of other drawbacks I'm sure you can think of, and benefits, of course, but this is a relatively simplistic approach that works quite well, and is used quite often. So something that's a little bit more flexible than trees, as we talked about earlier in the lecture already, is what's called a finite state machine. And here the big kind of functional difference is that a state can lead to many other states based on some kind of heuristic, some kind of set of things, right? So instead of having a yes or no, there's a little bit more nuance, right? Maybe it's some probability, some either uniform, maybe it's contingent on more complicated conditionals, and you have multiple states that you can go into. Maybe external things can affect the state as well, and so ultimately these things get represented as graphs rather than trees, which trees are graphs, but all good. So kind of as an exercise you can kind of try to do, right? Think about think about a first person shooter enemy, right? And create a finite state machine for that enemy AI. So you can use diagrams.net, which is, or Figma or whatever you want. This is from the old lectures, so whatever. Do this on your own, like there's no class, or you can post it to the channel if you'd like, and we can all talk about them there. But yeah, so you can use this, and you can sort of have states as the functional state of an enemy. So for example, you could be wandering, or you could be checking the fridge, or you can be eating a sandwich, whatever. A lot of options. I don't know what kind of first-person shooter you're making, but it sounds delicious. So generally speaking, transitions are things that can happen in the game that get the AI into state. So for example, I'm eating a sandwich, sometime somebody entered the room, and now I'm in the state of embarrassed. So, right? So there's a lot of interesting things that the environment can do to my state. But right, state transitions are not decisions to be made. In fact, the actual decisions that are made are kind of layered on top of this in some way. And if you're interested in that in a kind of deeper fashion, I recommend you look at what's called hidden Markov models, because hidden Markov models, we have observations, right? Things that are happening that represent some underlying state. Like for example, I'm eating a sandwich is a condition, is an action because of a hidden state, and that hidden state is I'm hungry, right? And so I'm hungry could result in eating a sandwich or eating I don't know, a piece of salami. Either way, I'm fulfilling that underlying hidden state that is not directly observable. So hidden Markov models, very cool, very much used in natural language processing for things such as kind of like hidden Markov models for NLP. So yeah, cool stuff. Right. What are the benefits of FSMs? What are the drawbacks, and what does the code look like? So feel free to take a minute, pause, think about this before I go on. Right. But so one of the benefits here of a finite state machine is it's quite exhaustive. Right. We can sort of represent all of the different states that we want to represent, and it's relatively deterministic too. Right. While these game systems are complex and say you have a lot of dynamic things changing all the time, for the most part, knowing you can kind of track back why a state transition occurred. It's not like some random thing that happened, right? Like a boulder came in the door and you ran away. You can sort of map the actions and the behaviors that resulted in that. The drawbacks, I think, are a little bit more nuanced, and the big issue, and it's really the same as decision trees and so on, or anything that has this sort of discreteness to it, is coverage, right? Like the reality is that not all state spaces can be represented as finite state machines. And so this gets a little bit difficult to do, especially when your state is a continuous variable, right? So what if your state is a position in space, an XYZ position? You can't actually represent that right away as a finite state machine. You have to take your space and you have to sort of turn it into quadrants or regions. And now you're inside of a region, like imagine a voxel grid, and being in that voxel is a state. You can't just be an open space. Like finite state machines do not work in this continuous fashion. There are other issues with finite state machines that get a little bit nuanced. For example, whether or not the state is affected by prior states, right? So, for example, if I went to the store, if I went to a restaurant, then I'm not going to get hungry because I ate before, right? So it's hard to codify this in a state machine, right? Because the idea of I'm no longer hungry because I ate has to be represented in some underlying variable that then represents that transition, almost like a counter. I ate, and so now my hunger goes to 0 and is incrementally growing. And when that environment raises it above a certain threshold, then that transition occurs, right? So it's a little bit weird, and actually in AI, often this is kind of referred to as the Markov property, right? Because if you're looking at a state machine in the form of a Markov model, which is this sort of state machine with a Markov assumption, the Markov assumption is that a particular state transition is independent from other previous transitions. So being in a state and taking a transition is unrelated to any other previous state you've been in or any other previous transition that you've taken, which is a drawback, right? Because most of life isn't like that, right? If you play a game with your friend and they cheat, you might not play the game with your friend next week because you know that they're a cheater. Something has fundamentally changed about your state machine in a way that is not represented, that breaks that Markov assumption, right? We don't have zero memory. We remember what happened in the past. The code for an FSM is like, it looks like a graph. So it's a little bit more dynamic. It's a little bit less, I think, efficient than, say, a binary tree or a static array, right? Because you have to be able to represent some arbitrary number of edges off of a particular state, and often those edges may be even dynamic as things get added or changed as you go through. So, finite state machines, fun stuff. But the F is capital in finite state machines. It is a finite state machine, so it cannot be infinite, and most things in the world are infinite. So let's talk a little bit about production systems. It's interesting because I'm not too familiar with the production system definition as used here, which is more of a computational system, but I've seen production systems in the context of general AI and like set theory, in the sense that a production system is one such that you start with a set of axioms, and based on those axioms you have certain rules or or production rules, as we'll talk about. And those production rules off of an axiom then result in new theorems. And so you can imagine kind of composing a string with certain rules and things like that that can only produce certain strings but not others. We'll talk about that here. So a production system, just like as I mentioned, and we're going to use a very different set of terminology than what I just used, because the terminology I'm familiar with is from the mathematics side. But a production system has a set of productions, which is sort of a condition action pair. It sort of is like, here's something you can do. It's almost like a transformation. Like here's a circle, and I can draw a line inside the circle, but I can't draw a line outside the circle. That's like a production, right? A working memory. So this is the current state. In the case that I just explained, that's the circle, that's the line. Like those are states. This is the world that we're applying transformations to. It's almost like, imagine a chunk of Play-Doh. You can muck around with the Play-Doh and turn it into different shapes, but you can't add more Play-Doh or remove Play-Doh. It's just this Play-Doh thing, right? And so how many different things can you produce it? It's a finite number of things. You can't turn the Play-Doh into anything. But you can also, it's not a finite, it's like actually an infinite set of things you can do, but it's bound in some way. There are certain things you cannot produce from that. And a production system generally has this sort of cycle, right? As I mentioned, in the case of the Play-Doh, I can do a thing to it, and then I have a new thing. Then I have to do another thing, and I have a new thing. And all those things are valid, and all those actions are valid and sort of independent. And so it's a cycle where I have a chunk, I make a transformation, I have a new chunk, I make another transformation, that's a new chunk, right? So it's this sort of recursive, or better explained, it's an autoregressive type of set of things. You're sort of self-referencing this. And this is, by the way, why it's interesting in mathematics. The reason it's interesting in mathematics is due to Gödel's incompleteness theorem, which kind of, you can break the universe by simply putting onto a card two sentences, which is, the statement below is false, and then the sentence below is the statement above is true, and you just get into the self-referential loop where you can break these production systems. In fact, so they're not mathematically complete. There are certain things that are provably true. They're true, but not provably true. It's a fact, but it's not something you can prove, which is a little mind-boggling. But I won't get too deep into my mathematical session here. So the recognized act cycle is quite simple. As I mentioned, you start off with some initialized state. In this sort of fundamental aspect of production systems, this is what's called an axiom, right? Like, this is something that's given to you as true. It's like an initialized state. Often it's just 0, right? If I add 1 to 0, it's 1. If I might subtract, then that's a theorem. Now, if I subtract 1 from 1, I get back to 0. So we know 0 is an axiom, 1 is a theorem, whatever. Cool. So the current state is maintained as a set of patterns in working memory, basically transformations applied to an underlying initialized state. And then the patterns are matched against these conditions of the productions, meaning, so for example, if all I can do is add 1 to a value and I start with 0, right, I can never get to 1.5, right? In fact, I can never get back to 0 because I'm going to add 1, I'm going to add 2, I'm going to add 3, but I can never go 1, 2, 3, 2 because that involves subtracting, and that's not included in my set of productions that I'm allowed to use. Multiple productions may match, right? So there may be conflicts where you do two things and they result in the same thing. And so there's no kind of guarantees on this. There's no necessarily rules about the rules, given that they're the rules that you've given them. And then the process terminates when the context of the memory do not match any rule conditions. And this is kind of a more of a computer science thing, because often we're trying to get to a terminal state, but production systems often don't have terminal states, right? They're defined by these rules that, and in a way, that's sort of why they're interesting to us here, because the state of the environment may change, and all of a sudden the production system may get you into an inconsistent state based on the rules of the production system, because something else is mucking with your stuff that's not inside of this. So know that a truly encapsulated production system can never terminate, but in the case of AI and for game development, that's not really true. What production systems have you seen? If you've ever used Alexa, you're using a production system. these things are not they're not that clever. Like when you're using a lot of these productions, these commercial grade systems, they need to be robust and predictable, and so often they rely on these kinds of systems that involve sort of goal-oriented planning and things like that, versus true RL or reinforcement learning based learning things, which can be kind of stochastic and often random and not make any sense. So there was a system a long time ago called ELIZA, and by a long time ago, I'm talking about like the 80s, 90s maybe. It's kind of fun if you have an iPhone and you ask Siri, who is ELIZA? She'll tell you a fun story. So ELIZA was kind of a expert-based system for speech and for, it was like a chatbot. It was one of the first really interesting chatbots. And it was really surprising just how deeply, right, like there's the whole Alan Turing imitation game, the Turing test of, can you talk to an AI for 20 minutes and it maintain an interesting conversation, which I think is an unfair test because most people I know can't maintain a 20-minute conversation that's interesting. But regardless, that's the test, and it's surprising how close ELIZA was just a few, basically, it's a shit ton of if statements, and it was able to trick a lot of people into this sort of, this is like there's like some kind of sentience on the other side of the line here. So yeah, in the 60s, not even the 80s. So it's the 60s. It was meant to emulate a psychologist with a patient, and it was pretty effective. I guess Weizenbaum later became a jerk. So oh well. Yeah, slides. Okay, but how does it work? So this is from his paper. Input sentences are analyzed on the basis of decomposition rules, which are triggered by keywords appearing in the input text. Responses are generated by reassembly rules associated with selected decomposition rules. So basically, a lot of if statements. That's what that means. So the technical problems is like identification of keywords, which is a little hard. This is actually an ongoing issue if you've ever used an iPhone or any kind of phone with a keyboard. You've misspelled things and you had to autocomplete them and so on. The discovery of minimal context, I think that was a really hard thing. This is still an active area of research. The context of, if you've seen things like GPT-3 and transformer models, what they've essentially alleviated is the context. So now you can use a million words as the context. And when people are talking about the context in NLP or any kind of system like this, what they mean is if there's an action that you've taken or a state transition that's occurred, and it's surrounded by a lot of other stuff. So like say you record somebody playing a game and you take out one of the actions and you try to predict what that action is. That action is likely going to be based on all the other actions and states that they've been exposed to. And that's what's called the context. So you can see as the context gets bigger, the computation that you need to actually process that context gets massive as well. And so you have to constrain it. And that's actually what a lot of transformer models did recently, is by allowing the model to leverage what's called an attention mechanism to pay attention to specific aspects of the context in kind of intelligent ways. For example, when you're translating a sentence from one language to another, the ability for one word to be contextualized based on certain words in the input sequence, right? Because you're not going to just, translate each word independently. You need to have kind of a deeper understanding of what the sentence means. Like, for example, certain words have multiple meanings, like the word plant could be a plant, or it could be a factory. And there can be a lot of, or a plant, like a person who's been planted there. So there's a lot of different kind of connotations that come along with a context. And that's exactly what the context means. In the case of AI for us, it's really about, well, what's the state of the environment? What is the state of my mind, of my AI, and potentially other things that is taken into consideration. Right, you also have to kind of consider the transformation. So how you can transform one thing into another. But this is generally going to be encapsulated by your state transition model, be it a finite state machine, Markov model, or something else. And also you have to sort of generate responses that are interesting in the absence of keywords. And then how do you create a generative language model? So gets hairy. So The keywords, they might have a rank or precedence number. So this is something that is now kind of more modernly discussed as a vocabulary. So you may have like a vocabulary of 10, 20,000 words that are codified down into individual values. So you take an input sentence, you tokenize it, you turn it in. This is a whole deep subject of NLP, which I happen to have a bit of background in, so this is a little bit out there. But long story short, right, you have these keywords and you have these transformation rules that are able to apply to these values because you're no longer dealing in words, you're dealing in these vectors of words or these vectors of values that are often just like summed up and stuff. It's kind of surprising that it works at all. But yeah, and there's a lot of other issues, like for example, what's the most important keyword in a sentence? What's the thing to really focus on? This is in the modern context has been addressed by attention models, for example. Right, what's the appropriate transformation? What is the transformation to use? And then how do you respond intelligently when the input has none of the keywords that you're using? This happens a fair bit, right? How do you deal with a word that's only been in your data set like once or never? And how do you deal with that word or an unknown word, right? Like can you kind of impute a meaning to this word even though you've never seen it before? And if you think that that's kind of crazy, every one of you has done this at some point because that's how we learn our language, right? We learn language by hearing people talk or reading and then kind of making sense that based on the context of the sentence, this word I don't know means something, right? And so it's quite an impressive feat, right? So here's an example transformation. So consider the sentence, I'm very unhappy these days, right? And then somebody only understood I am, right? And responded, how long have you been very unhappy these days, right? You just apply the template, right? So you can have some kind of way to reassemble. I am blah would be like, how long have you been blah? So this is a template independent of the word blah. So this is one example transformation. But here's another more slightly complicated example, right? It seems that you hate me, and the words you and me are understood, and the template composes it down into 4 parts. It seems that you hate me, and then the reassembly rule may be what makes you think I hate you. And so you can kind of see that like it's almost like this game you play as a kid, right? When somebody says something, you just kind of transform what they say into some other version, and you eventually just get really frustrated with you. But it is a way to carry along a conversation, and it's surprising how effective this is to trick people, right? And more modern versions of this are not that different than this, except instead of having this decomposition into a template, that template is this dynamic probabilistic model that does a little bit more reassembly and context and so on, but the fundamentals are about the same. So how can you make the program fail, right? Translation is a great way to do that, right? So machine translation is getting a lot better. In fact, I think even at the time that this slide was made, since then, machine translation has kind of grown in leaps and bounds by way of a recent transformer model by the name of BERT, or what's called bidirectional decoder encoder, right? BERT, bidirectional encoder representation transformer. So it's just essentially it's going in both directions, because in the context of a translation model, you want to look at the beginning of the sentence and at the end of the sentence. You might not be doing this for the translation, but when you take a sentence, you want to sort of, for each word, look at the words before and after. And BERT was one of the first models to do this. Whereas before, you had like n-gram models and sort of probabilistic things, or what's called recurrent neural networks, that sort of encoded the sentence down into a representation and then sort of decoded it into a different representation, into a different sentence. And so, yeah, it's a lot of progress has been made here than even at the time that this slide was originally made. But there's still a lot of improvement, right? But the big leaps and bounds on machine translation came from sequence to sequence models in the form of RNNs, and then more recently with attention models, such as, well, sequence to sequence with attention, and then later transformer models as well. So pretty cool stuff. But I think that the point of this slide is to say that these finite state machines, these transformations, these production systems have kind of historically failed at things as complicated as translation. So that is true. Those things have been very ineffective. So that's the end of this part 1 of architectures. Stay tuned for the next part, which I'll do in this. I'll do in a separate video, actually. See you then.